Thanks for introducing me, and it's very nice to be back in Ireland where I've been so often. But first I would like to acknowledge the co-authors that are next to me in the office and the people from the Robust Milk team, a EU project that I'm coordinating, and the Global Dry Matter Initiative that I come back to later. After the talk of the ministry yesterday, and after hearing Victor Aloui about the situation in the poultry breeding, it's not a surprise anymore that we are desperate to select for feed intake and feed efficiency in cattle as well. It's to do with the discussions about food, forest or fuel. We have to produce twice as much food on half the number of hectares. It's to do with environmental issues, greenhouse gases, manure, but also obviously to the feed cost at farm level. But in dairy cattle, we've always had this big dilemma that we can't measure feed intake in a progeny testing scheme. So therefore, we are not able to selecting this for this trait or improving our animals in that sense, although we know there's a lot of genetic variation there. So in this talk, I try to take you with me on the route that we and several colleagues of mine are taking to beat this dilemma. And part of the solution is genomics. And it's all work in progress, so it's not a finished piece of work. We're not selecting it for tomorrow, we're not selecting it for today, but maybe there's a light at the end of the tunnel we've been in for the past 20 years. So the outline of the talk is I start with the classical way. We know that a lot of the food a cow eats is going into production and maintenance. So how well can we do by predicting feed intake or feed efficiency from those components using traditional genetics? And then how can genomics help us? And finally, I try to picture the future perspective that we see in front of us. And we don't know if we are there next year, it might even be 5 years, because we know we're on the right track, but we don't know what hills we might still have to take. So the future perspective might be for a progeny-tested bull or a genomic-tested bull. So first, the classic genetics. What we did for this little project was we compiled all our data we had in the Netherlands on feed intake. We managed to get nearly 2,000 lactations with feed intake, ration, chemical composition, and live weight recorded. These were not full lactations, and there was a very messy data set in some cases, so it took a lot of effort to compile them. In fact, I think we had another 800 records, but at the end we couldn't use the records from that farm yet because there were some components missing. And the first question we addressed was, can we predict energy intake, or better, can we predict feed efficiency from metabolic body weight and energy in the milk? And can we make a breeding value from those traits for feed efficiency? So when we estimated the genetic parameters, and assuming that we estimated them correct, and there's obviously a big assumption, this is the accuracy of the breeding value for 3 different definitions of efficiency. At the bottom, you will see the 2 ratio traits, and from the yield traits and the live weight traits, we did get an accuracy of about 0.4, which is not bad and probably a good start. When we defined it as a linear combination and a linear trait, we were even getting an accuracy of 0.7. If we would record on some of the daughters of the bulls, maybe in a research herd or somewhere else in a mowed progeny testing scheme, we would increase the accuracy a little bit. So that made us relatively excited, and we thought, okay, we can make a start. So we talked to CRV, and we were getting the linear type classification data and the data on the 305-day yields. And we estimated the genetic correlations between energy intake. As you noticed, we moved from energy intake or from feed efficiency to energy intake, or dry matter intake. And that was because we discovered that defining the breeding goal for feed efficiency is quite complicated, because you also have an economic breeding goal, and it needs much more work to integrate these two. You might have very feed efficient animals that are very economically poor. So let's say we moved the direction a little bit. Let's try to predict that trait that we are missing in establishing the right breeding goal. These are the genetic correlations between the traits and energy intake. We also extended it with another period in the lactation. We had to take a period because otherwise we'd be losing too many animals. And we found extremely high genetic correlations with the linear type traits, especially stature and chest width. Obviously, these are the traits that a lot of breeders like, big, tall and big cows. I think actually that they might be a little bit too high. There were some red cattle in the data set, and they might have changed these a little bit. If you look to the previous data set, the genetic correlation between feed intake and live weight was about 0.52. So it might be a bit an over-exaggeration, but certainly milk yield and live weight overall is predicting feed intake quite good. So if you go very blunt and say, okay, we've got the genetics, now we can make an index and we can estimate a breeding value for bulls for feed intake, and that's being a bit blunt, that's what we did. We predicted for all the bulls in the Netherlands a breeding value for dry matter intake. And we predicted it using milk, fat, protein, stature, and chest width. The genetic parameters predict that we have an accuracy of about 0.8 using this prediction formula. Now, I don't think that might be that high, but clearly we see there are large differences between the bulls, simply based on their production and their size. And even that is very relevant information for breeders. But we are not publishing this is just part of the research project. For me, the important message was that we can explain about 2/3 this squared of the variation by these traits. And since we explained 2/3, we have to try and use genomics to find the other third, because that's important. We want to identify the cows that have the same size, the same production, but are more efficient. That's the net efficiency we are interested in. So, go on with genomics. What's that going to offer to us? We can try and identify individual genes. And in the Robust Milk project, we did so. We looked at the traits live weight, body condition score, dry matter intake, fat protein corrected milk. There was data from the Langhill herd in the UK, Chagger's data was in there for Moorpark, Swedish data was in here, Dutch data was, I think, in here. So again, a nice combination. We genotyped all the animals, I think roughly about 1,000 animals, and we looked at significant SNPs. If you focus on, in total, in this whole feed complex, if I try to call them, there were about 500 unique genes in vicinity of the SNPs that were significant. And 27 of them were, for example, close to body condition score and dry matter intake. If you looked at the biological processes the genes were involved in, they were involved. There were 32 genes overrepresented in this set of 500 genes, and they had to do with smell, taste, and pheromones. Obviously, biologically very exciting for a scientist who's been working on feed intake, body condition score, and fertility. And now, suddenly, this process comes up out of this cloud of many significant SNPs. There were 3 SNPs for dry matter intake in there. One on this chromosome related to tryptophan. It's a gene very much involved in motivation, and feed intake in several species. Insulin genes, there's a lot of literature how the high genetic merit cows have become more insulin resistant. And there's some very fake process related to epidermal growth factors. Now, I could have been very excited about this, and I was excited, but I don't think that's the answer for you today. Because I wouldn't like to sort of start selecting for some of these genes, or tryptophan, or insulin genes. And all those single genes explained very little of the total variance in dry matter intake. So I don't think that's an important route to go. And obviously, then I would have to spend the rest of my time on writing patents and that sort of things, and that is a complete waste of my time. I'd rather do other things. And let's see genome-wide selection. Where's that going to bring us? We do have the predictors. We might have some genes, but I think we should ignore them. How far is genome-wide selection going to bring us? In our initial data set, and there was a study done before the others, we only had 600 cows there. And if we look at the accuracy of genome-wide selection using those 600 cows, the 50K SNP, then we were only getting, I think it was 0.36. So you can be happy or unhappy about that. If you don't have anything, it's actually pretty good. And you can start selecting about that. But obviously, it's not good enough, and certainly we should continue this. This work was done by Clara Fabia from Melbourne. Now, I think in that area, phenotyping is still king, but every country has far too little data to do anything, and we started to collaborate. I was over in Melbourne, and I managed to send Yvette de Haas, my colleague, to Melbourne, and work with Ben Hayes and Jenny Price, and we put some first initial data together. Just let's see if we can get a feel, can we put data together, and is it going to work? Also, the data from My Coffee and SCC from the Robust Milk Project was included in that analysis. Interesting to see that in all the bulls we had genotyped were in the pedigree only about 40 bulls in common. If we wouldn't have had genomics, there was no point in combining this data. So we estimated the genetic parameters and the genetic correlations between the three very small data sets. Heritabilities were large in each data set. Genetic correlations were estimated very poorly, and that's what you would expect. But also, they were good enough to try the effort, but it's not that you would expect a lot from combining the data. You know, you're combining a few hundred animals on one side and a few hundred animals on the other side. And the genetic correlations are not one, so we don't expect a huge increase in accuracy. But more important, this also shows that we need a multi-trait model. If we actually were combining the data in a single trait model, we were losing a lot of accuracy. So that's what Jenny and Yvette did. And we got a slight increase from the within Australia analysis to the combined analysis. The UK were very lucky because they had a high genetic correlation. They got even a higher increase, and we were getting a very small increase. When I looked a little bit more in detail to our results, we did have a lot of variation in the validation sets. And one of the validation sets showed a drastic drop in accuracy when we were combining data. And for me, there was an important lesson there in saying, be careful when you combine data. Maybe the data is genomically different, and we shouldn't just simply think that adding data together and putting the genotypes together is always improving the accuracy. However, overall, we were pleased. At least we did get an increase, although it's marginal, but we know this wouldn't have been the end of the road. So last year in Stavanger, we had a meeting with people, industry people, how should we proceed from the Robust Milk Project, and this area was identified as being the most important one to see if we could set up collaboration. So that's what we've done. From the 3 core partners with feed intake records in the Robust Milk Project, we had already started the collaboration with the Australasian group working in this area. 2 other groups in Europe joined the initiative. There were some industry people from the Netherlands, Spain and Ireland, and I think there's one coming in on board from the UK, putting some cash money in, that really peanuts, but it's very important to make the clock tick. And with collaboration with the USDA experiment that Mike Tehar is organizing that, and with the Canadian people. And we decided, let's see if we can all put in kind effort and money, genotypes and phenotypes together to build a genomic prediction. The key research questions are, what is the genomic similarity between the different data sets that have been put together? How can we combine the phenotypes and standardize them and come to a common analysis? And finally, can we predict a genomic breeding value for feed intake from this combined data set, and how well does it work? And obviously, it's after that that we know where to go. Last week, we actually were doing quite a bit of this. We had a very efficient week in the Netherlands with the people putting together the phenotypes. At the moment, we have about 7,000 cows with somewhere during the lactation feed intake measured. Here you see the 7,000 cows. parity 1, parity 2, parity 3, and where there is a color in that week after lactation, we have a feed intake record. So it's very scattered and very difficult to combine. There will be animals dropped that might not have sufficient feed intake records, but obviously for Guru scientists, this is a brilliant challenge to work that out. There are the cars from Australasian experiment and a total of lactation. And Donna Berry has put that together last week and the people before that. In terms of genotypes, I think we've got about just over 6,000 genotypes. Most of them are the 50K SNP. We've decided to impute from the 50K up to the high-density SNP, and we're doing that in two parts. One is the Australian-European connection, and I think it's the Northern American connection, all using their HD SNPs, and that will make we have a combined data set at the end. And in the next year or so, or 6 months, we have the challenge to see if we can combine this and provide the answers. So we've got predicted traits based on classical genetics and genomics. We ignore the individual genes. We might have a genomic breeding value based on a certain size reference population. So where is that going to bring us, and how do I see we hope that's going to combine in the future? And I think you shouldn't take the numbers too absolute, but we had, for a progeny-tested bull, we do have all the records on type traits and on milk yield. We do get an accuracy of 80%. If we would have included the genomic breeding value from the Netherlands, we would have seen hardly any increase in the reliability. But we have more of the real thing, I like to call that. We've got more feed efficiency and feed intake in there, and we are more capable of identifying those cows that have the same amount of milk and the same live weight, but still eat less. So therefore, the amount of the real thing we are looking after is increasing, but the total reliability is not increasing that much. If you would have taken the Australian, UK, Netherlands DGV, we should have seen a very slight increase in the DGV and hardly any improvement. If we predict, and that's obviously pure predictions, we don't know how much we're getting, we hope that with the DGV coming out of the Global Dry Matter Initiative, we, and obviously many other countries, should be able to increase the accuracy quite a bit, and also being able to select better for the real thing. How is that going to work out for a genomically tested bull? I apologize for the different slides, or all the lines. But let's take the example when we don't have a reference population with feed intake on cows. We go there and we only have the predicted traits. We come up with an accuracy of 0.6 based on the genomic proof. You're losing something from the progeny tested bull to the genomic proof. So that's also the total accuracy, and that's this line we are getting. If you would have taken the Dutch reference population or the UK reference population or the reference population in some of the other countries of about 600 cows, we might have get an accuracy of about 0.35. You could have combined that with the genomic breeding value for the predicted traits, and you would be stuck between about 0.6 to 0.63. What do you hope to do? And let's assume that the Global Dry Matter Initiative, we only thought about the name last week, so some people might have heard that for the first time. If that has a sort of effective number of cows measured with feed intake about 6,000, maybe it's only 4,000, we hope that our genomic breeding values based on the cow reference population is increasing quite a bit, up to whatever. I'm not sure if it's realistic, but we hope so. Combine it with the genomic breeding value for the predicted traits, and then we end up optimistically predicted here with even a high accuracy for the genomically tested bulls. But this is what we're going to find out over the next year or so, and I think it's setting a nice route forward. So in conclusion, Selection for feed efficiency is extremely important. I think we've got a challenge there, producing twice as many food on half the number of hectares and half the input we have. It would have been impossible a few years ago, and I actually did my PhD in this subject, and I thought I'd never come back to this issue. But see, here you go. With genomics, there will be a real prospect for the future. There might be a light somewhere at the end of the tunnel. With yield and type, we might be able to make the first step, but that's not identifying the net efficient cows. That's identifying the cows that give a lot of yield and have a small size. But genomics should help us to identify those net efficient cows. This might give us about 60%. Hopefully, we might be able to get another 20% on top of this. To put this all in the breeding goal is more complicated. And last week we had, for example, a discussion among the project team. And I know in several countries we are discussing this, also in the USDA, or in the Mike de Haas project. And I think we're going to come together to discuss how we're going to deal with the issue of energy balance, negative energy balance. How should we treat live weight? What's the economics versus the energetics of different traits? For example, the economics of fat and protein is different than the energetics of fat and protein. So how much would you like to select for the ratio between these based on feed efficiency, and how much would you like to be directed by economics? I would suggest by the economics. However, overall, I think phenotyping is still king, but it's the collaboration is leading, and it's not the king. And with that, I would like to conclude my presentation and acknowledge all the people that are involved in this work. Thank you.